Hello friends, welcome back to our channel. So today we'll see one more concept in discrete mathematics, that is a predicate calculus. So in our previous session we have discussed about various propositions and propositional logics, truth tables, etc. all comes under the statement calculus. But here we'll be seeing about the predicate calculus. So there is a slight difference between a proposition and the predicate. So before going to that, let's start the session, the introduction, and what are the different quantifiers in the predicate calculus. So let's start the session. So predicate calculus. So as the name itself indicates, this predicate calculus will be having all the predicates, right? So previously it is a statement calculus, so we have defined a statement which we are calling it as a proposition. But here we will be calling it as a predicates. So what is a predicate and how it differs from the proposition, right? So this predicate is also a statement. It is also a statement with a variable. Right? So if you substitute any value to a variable, then it becomes proposition. Simple definition, right? Simple definition. So predicate means it is also a statement, but it will be having some variable. Instead of value, there will be a variable. So I think all of you know about some knowledge of programming. So in that we'll be studying about a variable which can hold the values, right? So if any value given for that variable, immediately that predicate will be treated as a proposition. For example, let us take an example. See, x is prime. So this is a statement. Okay, this is a statement. So, but it's not a proposition, because proposition is a statement where we can have either true or false. But in this case, x is a prime is a statement, but we can't decide whether it is a true or false until you give some value to that x. So this we call it as a predicate. And if you substitute a value for x, for example 5 is prime, now you can say the truth value of this particular statement is true. Okay, definitely it will be true. So if you substitute some values to this particular variable, this becomes proposition. This becomes proposition, right? So this is a difference between a predicate and the proposition, right? So proposition, we are directly giving the statement which gives either true or false. But coming to the predicate, instead of giving the value directly, we are taking some variable, so that based upon the value that will becomes the proposition, right? So x is a prime. Now see, this x is called as a subject. So where we are substituting some values, and the remaining is prime, or anything, any other sentence other than subject, we call it as a predicate. Right? So x is a subject. So now the predicate will be having both the predicate as well as the subject, right? So usually this subject will be represented with lowercase letters, and the predicate will be represented with uppercase letters. So this can be treated as some X, this can be treated as some uppercase letter. I'll treat it as a P because here it is a prime. Okay, based upon the statement we can give the letter alphabet. So here I am giving as a prime, so I am giving it as a P. If I take it as an even, I may be taking it as a E, capital E. Now this particular predicate, okay, this particular predicate can be represented as capital P of X. Capital P of X, where X is a subject and P is a predicate. So just remember the representation of any predicate will be in terms of capital letter which is representing the predicate and a small letter which represent it as a subject, right? Now X is a prime can be represented as P of X. P of X, where P means it is a prime, X is a prime, right? So hope you understood what is a predicate, right? So there will be some sort of variables inside the predicate. Now if you are saying that X is a prime, now what are the values of X? So the truth value of this particular predicate, what's the truth value of this particular predicate? So that depends upon the value of X. That means X will be holding some range. Okay, X may hold the range of values. So here we can represent the scope of X. So where it can be used. Okay, so this will be represented in two forms. So in a form like a quantifier. The scope of a predicate can be represented by using a quantifier. Scope means up to what extent the values can be given for the given domain, right? For X, what is the values we can give, right? So scope of a predicate, this particular predicate, scope of this particular predicate will be represented with the help of a quantifier. This is most important, quantifier. Okay, so there are two categories of quantifiers. So one is universal, next one existential. So universal quantifier and existential quantifier. So two quantifiers, mainly these quantifiers is used to give the scope. That means up to what extent that predicate can be used. So we'll see about these particular quantifiers and then we'll go with some examples, a few examples, and we'll stop. So till now, hope you understood about what is a predicate and how it differs from the proposition, right? So now universal quantifier. Universal quantifier. And universal quantifier means for all the values of X, the predicate becomes true. So for all values of X, the predicate P of X becomes true. So if you consider any value of X, the given predicate will be true. Okay, and the representation of this universal quantifier will be in this format. Okay, so for all X. Okay, so reverse of A is represented with a universal quantifier. Let me tell you an example. See, if I am having some predicate p of x, which is x square greater than 0. This is a predicate. P of x is equal to x square greater than 0. Now, what is the quantifier here? So, with the help of quantifier, how this truth value will be true, right? This predicate becomes true. So here we can say for any value of x, the x square becomes greater than 0. Yes or no? So for example, if you consider x is equal to 1 or x is equal to 2, then x square, which is nothing but 4, which is greater than 0. Similarly, if x is equal to minus 3, then x square is equal to minus 3 square, which becomes 9, because minus minus plus, minus into minus becomes plus. So 9, which is again greater than 0. So for any value of x, this particular predicate becomes greater than 0. So this can be represented as, for all x, p of x is true. So you are using some quantifiers to represent the predicate when it becomes true. That means the scope of the predicate. So once again I am repeating, quantifiers are nothing but telling the scope for these predicates. Right? Yes. So hope you understood this one. So always, for always x square greater than 0. So for all x, the p of x will be true, because for any x value, this predicate becomes true. Now, the next category is existential quantifier. Existential quantifier. So here, not for all, at least one value of x, the predicate p of x becomes true. Not for all, at least one. That means some values of x, for some values of x, the statement or the predicate becomes true. So the representation will be in the form of this one, reverse of e. Okay, reverse of e. Now let us take an example. The same example, predicate x is prime. Okay, if you consider x is equal to 4, what happens? The predicate p of x becomes false. It doesn't become true. Okay, for example, x is equal to some 7, then predicate p of x becomes true. That means not for every value of x, but for some values of x, the predicate becomes true. So this can be represented as in this way. There exists some x where p of x becomes true. So this is also called as there exist. There exist. Okay, so universal quantifier is for all, and this is the there exist. Right? Now let us take one more example. For example, if the predicate x comma y, that means that two statements, right, is equal to some x plus y is equal to 10. Okay, this is the predicate. X plus y is equal to 10. This is the predicate. So how it can be represented with the help of a quantifiers? So for any value of x and any value of y, will this particular predicate becomes true? So for example, you can take x is equal to 5 and y is equal to 5, then obviously x plus y will be 10. Yes, but if x is equal to 6 and y is equal to 7, x plus y becomes 13. So for some values of x, for some values of y, the predicate x comma y becomes true. For some values, not for all the values, for some values. That means it may be if x is equal to 3, y becomes 7, then the predicate is true. if x is equal to 4, y is equal to 6, the predicate is true. Right? Yes. So, for all, not for all, I'm extremely sorry, not for all. So, there exists some x and there exists some y, then only this particular predicate becomes true. Not for all the values this predicate becomes true. So such that we have to find out the predicates and then we have to give the scope for that predicate with the help of the quantifiers. With the help of quantifiers. Right? So now let us see one example so that you can understand clearly. See, here we are having some statement. Okay, every programmer has a knowledge on C programming. Okay, so from that we can identify the predicates. So what is the first predicate? Some X is a programmer. Some X is a programmer. And the second predicate, Q of X, X has a knowledge on C programming. C programming. So how can we represent with the quantifiers this one? So from this statement, we have identified some predicates P of X and Q of X. And now from this one, how can we represent this one with a quantifiers? That means how can we give the scope for these predicates? So here in this statement, you can see every programmer, that means here X is a programmer, that means every programmer. So for all X, simply we can write for all X. Okay, for all X, if X is a programmer, then definitely X has a knowledge on C programming. So the same thing is here. Every programmer has a knowledge on C programming. So if then means implies. So P of X implies Q of X. So this is the scope we can give for this particular formula, predicate formula. So similar to our propositional logic or propositional formula, here we are identifying the predicates and just we are giving the connectives. And apart from that, we are additionally giving some scope for what, I mean, up to what extent this predicate becomes true, either for all the values or for some extents. So that's the only difference. So from the statement, we have identified the predicates, and from the predicate, we have defined the formula. So we'll see one more example and we'll wind up. So let us take this example. So we are having 4 predicates, P of X, Q of X, R of X, and S of X. So X is a subject, as we discussed just now. X is a subject, and he is here. The first predicate is X greater than 0. Second predicate is X is even. Third predicate is X is a perfect square. And the fourth predicate is X is divisible by 3. There are 4 predicates. Now we are having a different statements, so that we have to we have to write down the formula along with the scope for that predicate. Now you can see at least one integer is even. So obviously not all the integers will be even, right? So some integers may be odd and some integers may be even. So at least one integer is even. So here we have to use the quantifier there exists, not for all X. So if you write for all, that implies that X always, any integer, if you consider any integer, that will be even. But that statement is wrong, right? At least one integer is even. So what is that integer is even? So this one, Q of X. So for all X, there exists X, Q of X. So this is the formula along with the quantifier. That here we are getting existential quantifier. And the second one, So here itself they have given there exist. Obviously there exist means or it will be universal, existential quantifier for some values of x, a positive integer that is even. So here we are having a two predicates, positive integer and even. So what is a positive integer? P of x. So obviously write down here P of x, positive integer that is even. Not all the positive integers will be even, right? Some sort of positive integers will be even. So that will becomes AND operator. AND even means a Q of x. Q of x. So for some values of x, and here end means nothing but see, only few values of positive integers will be the even numbers. Only few values of positives will be the even numbers. So you can simply remember that if you had some if and then, that means it implies then you will be getting for all, and all the remaining cases other than or you will be getting this end connected. Okay. Now some even integers are divisible by 3. Some even integers, again we are getting the word called sum. So here at least there exists sum. So obviously the quantifier will be there exist. Even integers are divisible by 3. Even integers means q of x. So q of x are divisible by 3. Divisible by 3 means s of x. Okay. So not all the even integers divisible by 3. We are saying some even integers are divisible by 3. So some portion. So that will be n. Next, if x is even and a perfect square, so you can see here in this statement, if x is even and perfect square, then x is not divisible by 3. Here we are having a 3 predicates. X is even. X is even means a q of x. See, here you can see the operator and directly. And perfect square r of x. Okay. You can observe here, if then implies x is not divisible by 3. Not x is divisible by 3 is a predicate s of x. But here we are getting x is not divisible by 3. So we can write negation of s of x. Negation of x of x. So immediately if you got if then, we'll get the quantifier for all x. For all x. For all x, if x is even and a perfect square, then x is not divisible by 3. That will be true. Okay, just remember, if you get the words like at least, there exist, some, like this, you have to use the existential quantifier. And if you are having any word like if then you have to use the for all or every. Okay, if then or every. Just remember these points. Okay, so hope you understood this one. We have seen two examples. So similar to our statement calculus, similar to our propositional logics and propositional formulas, here also we will be having some statements, but with the variables, not with the values. So if the value is substituted for the variable, then it becomes the proposition. And apart from the propositional logics, here we are using some scope for the predicates when it becomes true. So two quantifiers we have seen, so which represents the scope of a predicate. So one is a universal quantifier as well as a existential quantifier. For all x, for all x means the universal quantifier, and some values of x, the predicate becomes true means there exists. That we call it as a existential quantifier. So I'll stop here, and if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.